Okay. No. I'm. That's just my notes. All right, I'm ready to go.
All right, we will start with the afternoon session. John Joseph and talking more about scattering.
Okay, so before I begin, just a couple of announcements. Some of you may have already seen I started a Slack channel just for discussion about amplitudes and the stuff we're presenting here, where you can ask questions asynchronously as they come up. So I'll be able to help you with that, especially if you have questions about references where you can learn more about various questions that have come up. I've added various reviews and lecture notes to the Wikipedia page, to the Google Drive that's linked to off the Wikipedia page. And I'll put in the Slack some annotation why I chose those and what you should look for in those. And I'll be adding more stuff to that as topics come up. Yeah, all right, that's it. Any questions? Any questions starting over from last time? Okay, fantastic. All right, so lecture 3. So what are we going to be talking about today? We're going to be talking about state sums, so unitarity methods. We're going to talk about gauge invariants, gauge invariant building blocks that go into full amplitudes, and we'll talk a little bit about graph methods. All right, so we're going to jump into 4 points now. And the first thing I'm going to talk about, as I said, is state sums. All right, and we'll set this up. Okay, so what did we find yesterday? We found yesterday that a process that has a fermion and a gluon, or a vector at least, 1, 2, 3. Let me give some indices, J, I, and A, right? At lowest order in mass dimension, we'd go something like this. Yep.
And there was one more mention that was the momentum contracted with the...
Yeah. So there was something at a higher mass dimension with more K. So I'm talking about the lowest mass dimension. Okay. And you might recognize this as like the on-shell vertex that you get for QCD or QED. Okay. And the color weights for same graph, said was generically some sort of Ti j bar A, where this is, so as I said, some arbitrary representation until we fix it to talk about something we actually particularly care about. Okay, so if this was just QED, right? So, what is this? What was this G? This was some parameter, right? So this is some coupling. All right, and maybe you normalize it according to how you care about normalizing things with some coupling here. So what's going to go into here? If this was QED, what would be showing up here instead of some arbitrary T, right? It would be the charge of these particles squared, right? That's what would be showing up here. Okay. What if instead of an electron running through with a photon, I had quarks running through, but with a photon, because quarks have charge, right? So something like this would turn into the q squareds for the quarks times the delta ij bar for the color index that's preserved, right? Because things can be charged in product representations, right? You know this from the standard model, right? So we're not just things that are in one gauge group necessarily, things can be charged in multiple gauge group. And this arbitrary structure has to encode that, Okay?
Why squared?
Or whatever. I mean, I don't know. I know why q squared, because I like relating q to m, and I like having m squared. But that's just me.
So when things are charged under multiple gauge groups, is that represented by like a single matrix or tensor?
Well, so you can have bicolored representations that are for products of gauge groups. Now, sometimes they factorize nice and cleanly. Sometimes they're much more complicated. But this is just like standard model stuff. So if you want examples of this, like go to like Peskin and Schroeder or Schrednicki or Schwartz or whatever, your favorite quantum field theory textbook is, and start looking at some of the standard model process calculations. Okay, and how you're actually representing particles that are charged in multiple groups. Okay, good. And this was just to set us up, because now we're going to calculate something physical. Okay, maybe you already know, based upon the two examples I just gave, what I want to calculate. What about E plus E minus going to some quark plus quark minus? Okay, so this is a 4-point amplitude. Okay. What's the mediator going to be? What's the mediator for this process? It's going to be a photon, right? So a photon. Let's consider a fixed helicity. So let's have plus minus plus minus. So this E plus coming in will have so in all outgoing convention will have plus helicity. The E minus will have negative helicity. Some quark plus will have plus helicity. The quark minus will have negative helicity. Okay, so. All right. Yeah.
Is it important that the mediator be massless here, or could we have the Z as well?
For the calculation I'm doing now, we're going to keep it massless, okay? And in fact, what I'm going to consider is the high energy limit. So we can neglect the mass of the E's and the Q's, because everything we talked about yesterday was kind of massless anyway. But I absolutely encourage you to go see what changes when you put masses back in. And what changes is what you mean by U bars and V's, not much else, okay? And what would change if we were talking about a process that had, some sort of like, SU2 sort of like, massive gauge, blah, blah, blah. Yeah, so our propagator would end up having a mass. That's pretty much what changes here. Yeah.
In the high energy limit that we're talking about, if we're above the muon mass, are muons and electrons the same in this method?
Are muons and electrons the same in this method? The same sort of scattering amplitude. Yeah, I guess so. So what would be different? What type of processes would let you distinguish between a massless electron and a massless muon?
I would expect it to be the same.
Well, all right. Let me. I'm actually not in that frame of mind at all. So let me think about that. Come back to you. There are absolutely processes that distinguish between electrons and muons, even when you don't care about the mass. I mean, even at high energy limits, right? So, for example, you don't get to have, your electron and your muon coming together at the same vertex, right? So there's a flavor conservation, but in terms of whether the S matrix, I believe the S matrix would be the same. So if I had like mu plus and mu minus here instead of E plus and minus, what's going to change? Yeah, good. All right. So if I had things with different charges, then I have different charges. But okay, good. All right, so what's the only cubic diagram I can write down at 4-point for this is something like this. And let's see, I'm going to call this K1, I'll call this K2, K3, and K4. And what else do I need to say? I need to give this like an I and a J bar for the color indices, right? Because these guys carry color, right? Okay, good. All right, well, let me also say this. So what I'm going to have you scatter is an electron that comes in, sorry, a positron that comes in with, positron comes in with negative K1, electron comes in with negative K2, right? Quark plus comes out with a K3, and the K minus comes out with a K4, right? So that K1 plus K2 plus K3 plus K4 equals 0. Okay? Right, just so I can use my out convention, right? Everybody's pointing out, right? So all this means is what's coming in, so I'm sending in something with a negative K1. Okay. Good. So we can write down a good guess with our rules. All right, that's it. Okay, right? We've got our, closed fermion lines with our fermion bilinears, right? And they need to speak to each other, right? So, this is a fairly good guess with our rules, right? And in fact, this is what you'd get if you wrote something down with Feynman rules. If you use the Feynman rules, this is what you'd get, right? For on the kinematic part, right? So the color part. Right? Okay, what about the propagator? What's a propagator be for, that guy? As far as I care.
I guess it's massless.
Yeah, it's massless. What was the propagator?
1 over L squared.
1 over LL. What's L?
Momentum of the
Right. So what is the momentum running across? K1 plus K2 squared. Right. So so this is going to be okay, and we call this S, the Mandelstam variable S, K1 plus K2 squared. Okay, good. So how do we check if this is consistent with what we understand for our theory, right? Given the lowest order mass dimension 3-point vertex we wrote down before, right? And the way we check if it's consistent is by doing a unitarity cut, okay? And so maybe you remember from the first lecture, I talked about, you make a guess, you fix on symmetries of the graph, and then you fix it to the cuts, right? And if you can't fix it to the cuts, what you're trying to do is inconsistent. Either your ansatz wasn't big enough or your story is not holding together, okay? Good. So this is a real simple example that I'm using because it illustrates 2 aspects of performing the cut. One is evaluating your mappings on the cut, evaluating your amplitude on the cut from as far as the mappings, as well as sewing together the pieces, the lower order amplitudes, to fix it, okay? And it's not gonna be too grungy. This is a real simple example. I mean, this was almost entirely fixed, right? So I debated whether or not to do this example because there are no parameters to fix. It either works or it doesn't work, right? The reason I'm doing it is because it let me talk about something that hopefully you all recognize as physical and might even be the type of thing you saw in like a quantum field theory class back in the day, okay? Yes?
Is the integer what you were talking about in the first lecture where you split a loop level diagram into tree level?
And at the level of tree level, it's just factorization on a channel. In the level of trees, so it'll be a one particle cut, factorization on a channel, okay? And at 4 points, when I only have one diagram contributing to my amplitude, like this, right? Why don't I have any other amplitudes? Because these guys are very distinct. I don't have, an electron quark vertex, right? From flavor, yeah? And this guy doesn't get to speak to that guy, this guy gets to that guy. Now, is there anything that precludes higher derivative contact terms? No, absolutely not. I mean, unless you measure it, or unless you've got some symmetry you're holding dear to your heart that's ruling something out, right? That you don't know whether they're higher derivative contact terms suppressed by some mass scale until you measure it. But so we're doing the calculation with the theory we think we have, right? And we're at least seeing if this is consistent with what we already know about, presumably, which is that guy that I've written over there, okay? So hopefully you're on board with the attitude we're bringing to this, and we're just going to carry out the calculation. So you see the bits involved with something nice and simple, and can imagine how to generalize this to more complicated processes. Okay? All right. Good. So our amplitude equals C n over S, right? It's C n over this guy, right? And so what's the channel we can cut? We can cut this one channel, right? It's the only thing available to cut. It's the only internal line. Is there a question? Yeah, so which C do I mean here? I mean that C over there, right? Good. And so this N is you know what? I'll just label it 4. Right here, the only reason I'm emphasizing an operator, I'm drawing the graph, is just so I had some line I could cut, right? Yeah, but it's that guy. It's that functional N over there. Yeah. Okay.
And there's no propagator in here?
Well, here's the propagator. Here's the propagator. Okay, but what we're going to do is we're going to cut the propagator. All right, now I'm going to explain what that means in terms of dressing the cut amplitude. Okay, and then I'll explain what it means in terms of sewing the lower order amplitudes. So what was the 3-point amplitude? The 3-point amplitude. So the 3-point amplitude, that was some fermion, some gluon, like J bar I A, equals this N3C3, right? Right. This was our 3-point, the full amplitude, gauge invariant. It's absolutely gauge invariant, and it's on shell, right? Absolute physical states. You need complex momentum for physical massless states. We're not going to worry about that. It's on shell. Okay, for it to not vanish, you need complex momentum. That's a detail. Doesn't matter. Okay, so now this is all that's going on here, but I want to emphasize that what you're doing is now we're going to address what happens when you sew, a 3-point amplitude with a 3-point amplitude. Now, there's only one graph when it's two 3-point amplitudes, it's only one graph, right? When I'm talking about cuts with more legs, there'll be more graphs that contribute to a particular one particle cut, right? Or I could cut multiple channels to start targeting individual graphs on shell.
Since we put labels on the C's and N's, which ones are we using?
Right. So again, right now, I'm talking about what happens to the 4-point amplitude when we cut it, okay? So, rules for addressing a cut. Cut diagrams. Okay? Because now we're addressing a cut diagram. Okay? And so what's going to be different than our addressing a diagram who's only on shell on external legs? The denominator, the propagator structure from the cut gives 1 for any on-shell cut line. Otherwise, you get an infinity, right? Because once I put S on shell, if I actually had S in the denominator, I have infinity. I'm looking at the residue on the pole. So really what I'm doing, I'm looking at the residue on the pole. The rule is you just turn any cut line into 1. All other cut lines, all other non-cut internal propagators dressed as normal. All right, so for example, let's say I had some sort of, some sort of cut of like a 1, 2, 3, 4, 5 particle, some 5 tree and a 4 tree, right? These propagators would show up as normal, but this propagator gets replaced with the 1 because it's cut, okay? And in general, for something like this, a bunch of diagrams will show up over here, and a bunch of diagrams will show up over here, and you'll take the outer product. I'll talk more about that in a second. But I want to get through this particular example first. Yeah.
So in general, how do you recover the information from that propagator that's turning into 1?
Very good. We'll get there. All we're doing right now is we're verifying. This isn't construction. This is verifying that our guess isn't wrong for the theory. It doesn't mean our guess is complete. As I already mentioned, there could be higher derivative corrections that aren't, that have nothing to do, that you could never see on a cut. Contact terms that you could never see on a cut. If you have a symmetry, so if they're required for gauge invariance, like derivative coupling with gluons, then gauge invariance is something that will bring them to the bear. Color kinematics will serve in the similar. If you have a symmetry, like an Adler zero for pion theories, that will force contact terms to show up. But in lieu of that, contact terms are showing up with an arbitrary coefficient that's unfixed, but is perhaps suppressed by a mass scale. Okay? Which is true in general. I mean, so we'll write down an action, like for the standard model, but it's only complete up to what we've measured, right? Up to the energy scales we've measured, to the precision we understand. There are all the higher derivative corrections involving those fields that could be there that we don't know about, right? And this is a perspective effective field theory. Yeah. Sure. Yes. So good. So when you cut a fermion propagator, you're putting it on shell, right? And so you definitely need to close your fermion lines. Okay? But I'll talk about completeness relation for fermions in a second, but first I'm going to do the completeness relation for gluons. And then you had a second question?
Yeah, I don't know that I believe you that these things should be equal.
Good. Yeah, that's okay.
Is there like a reason why we might expect them to equal? Like, I don't know what we're accomplishing by trying to influence that like a potentially offshore diagram equal to these two offshore diagrams. What are we?
No, so good. So what could I possibly be missing for the dressing of this graph from Feynman rules after I impose cut conditions are only things proportional to the channel I'm cutting. So those are the only errors I could be making, modulo Feynman rules. And that's equivalent here to a contact term. Okay? And this is, so you, the other, you were like, oh, you're simplifying, Feynman, you're gonna be throwing away information. I'm not throwing away information. What I'm doing is I'm pulling information out of my theory in a very organized and principled way. And so right now I'm talking about cut verification. But when I talk about cut construction, at the end of the day, you need to make sure you satisfy all the cuts, okay? If you know something about the power counting of your theory, how your theory scales, then that lets you know how many cut lines you ever have to take off shell before you've saturated the power counting of your theory. Because anything sitting above propagators goes down, right? Because you've got momentum in the bottom, right? So if you've got some loop, right? Some big complicated loop, right? So anything that looks like this, right? Anything that's sitting here has the most momentum downstairs, right? And so when I cut it all the way down, I get something that's inalienably targeted to this particular graph. But what I'm missing are potential contact terms. That's the only thing I've missed from Feynman rules. The only thing that Feynman rules could have been giving me that I don't have are potential contact terms. So I start releasing cut conditions and start talking about what happens. So instead of having, sewing this 3-point with this 3-point, I'll turn this into a 4-point tree. So I've released one cut condition, okay? And as long as I'm sewing into a 4-point tree, this is contained. But there's only so many of these cuts I ever need to consider before I've saturated the power counting of my theory, no matter what my theory is. And then I'm done. Okay, then I've recovered anything that Feynman rules for that theory could have given me. Okay? I just want to make sure, yeah?
So I agree that we could have the contractor gammas out there and that works out, but if we're working, let's say, not in the Feynman gauge, and this stuff up here is gauge invariant, but if we're not working in the Feynman gauge, I also expect a K-mu.
Right, but everything's going to be gauge independent, right? So I'm going to start from something, that's gauge invariant, right? Because that's gauge invariant, right? So I'm starting from something that's gauge invariant, and I'm applying on-shell conditions to it. So I'm choosing particular kinematic limits. Okay, so that's gauge invariant. I'm starting from things that are gauge invariant here, and I'm sewing them. So all my expressions are going to be gauge invariant.
So that whole is just, that is the gauge invariant choice of setting it to 1 there?
Yeah.
Okay.
Yeah. All right, so now I'm going to go through, and I really do appreciate all these questions. So if it feels like I'm rushing, it's because I have so much I want to tell you, and I've only got such a limited time, but I am really happy because it's really important for you to have a feeling for this, more than being able to calculate. I mean, you can always go to the references and get better at the calculation. What you're going to get from me is the thinking behind this, like what we're actually doing here, why we're playing this game, okay? And then again, ask me questions on the Slack, email me, stay in contact if you want to learn more about this stuff, okay? Good. Good. This was, all right, dressed as normal, but evaluated with cut conditions, cut on shell conditions. And I'll say more about what that is in this particular case in a second. Let me just say what happens to the numerator. The numerator cut is just the same, is just as normal, but evaluated with cut conditions. Right? And the color factor is just the color factor cut. Okay? So the color factor we haven't done anything to the color factor. Now, what do I mean by evaluate with on-shell conditions? Overall, with this expression, we're going to have delta functions enforcing on-shell properties for the cut leg. Okay, and so what's true is K1 plus K2 squared equals K3 plus K4 squared equals 0 on the cut. S-channel cut. Okay? Yeah? Good. So, just to make it unbearably clear, this cut amplitude is cut, S cut. It's the color times mu2, mu1, mu bar 4, gamma mu, v3. I keep calling it a nu. Maybe because I spent so much time in Northwestern, Right? And I mean, this is the overall momentum conserving delta function that I've just been suppressing the entire time. That's always associated with this for the external legs, right? So I don't need to bother writing it. That's what gives this equal sign. It's the 0 that's the cut condition. Good. All right. And I'm not even gonna bother writing this delta function anymore. It's just we're evaluating on cut conditions. We see there's a possibility. Well, let's just. All right. All right. So the question is, does this match?
So that's a delta S.
Yeah, delta S. We're putting the S channel on shell. Okay. Does this match the sum you get of the states, some overstates of our on-shell 3-point amplitudes? So specifically, right over here. So specifically, let me know if you can't read my subscripts. I'm just giving a subscript to remind myself that this is a positron, subscript to remind myself this is an electron, and then I have to label this internal momentum something. I'll give it an I. Hopefully nobody thinks that's a phase. It's just an I for internal, yeah? So I'm summing over states. States. Physical states. Physical on-shell states this gluon could take. This gluon whose polarization I'm writing very formally, right, in terms of formal polarizations, okay? Right, so it's, so there's some gluon, and it's got some state S. Remember, it's all outgoing convention, so over here, it's going to have a minus momentum I, right? It'll have some state S bar. Okay? All right, so this is, yes, good.
I don't understand what you're here at all. Just explain.
Yeah. So what I'm going to do is I'm going to take that amplitude, right, that I've written down. Yeah, the 3-point amplitude up there. Okay? I'm going to put one of them over here. I'm going to put one of them over here. Right? I'm going to give one of them this guy's states, and I guess this was what, E plus, E minus, and I'm going to give the other guy this guy's states, Q plus, Q minus. Okay? And I'm going to label my cut momentum I, which means that outgoing cut momentum on this side is going to be minus I. Okay? And this is a gluon, so it has some physical polarization states. If I was in 4 dimensions, I'd say, ooh, well, what is it when it's a plus? And this is a minus. And then what is it when it's a minus? And this is a plus. But I'm keeping things d-dimensional here, so I have formal polarizations. So I have to tell you how to take that state sum. And I'll tell you how to evaluate this in just half a second. Okay? But that's what I mean by summing over states, all right? Is that this, once it's on shell, this guy has to be physical, a physical gluon. But it doesn't have to necessarily be fixed to be a particular polarization, right? But this has to be complementary to that, and you have to sum over what is actually physical, all right? That was a great question, which you didn't explain anything. Well, now I've hopefully explained it a little better. Any questions before I start evaluating this? Because I think it'll be clear too once I start plugging things in what I'm actually doing. Good. So, how do you sum over formal polarizations? Where's Dimitri? All right, raise your hand really tall. Everybody turn around and look at Dimitri. Dimitri knows everything there is to know about summing over formal polarizations and exposed tricks that many of us wish we knew a long time ago, but we're very grateful for tricks that Dimitri taught us. So if you have questions about this, come speak to him, okay? Well, he's going to be around Tazi longer than I am. So, all right, so you use the completeness relation. Oh, did I hide? Oh. Here, I'll try to write this in a way that's writable. Completeness, complete. Okay. Okay, so let me explain this. When you've got formal polarizations, they're dotted into something. All right, so pry apart the dot, and what's left, sitting right here, is some epsilon mu with some momentum. The momentum in this case is going to be I on this side. You'll also have an epsilon nu for the polarization that's dotted into here with the negative I, right? Negative I. Yeah? Good. And we're going to sum over the states. And what the sum over the states is for gluons is something beautiful, and eta mu nu, we love this beautiful eta mu nu, and something horrendous. And yeah? This, wahaha. So this is the gauge independent. This is the gauge independent projection operator. But I have introduced gauge dependence in the form of this. So I haven't told you what the Q is. Let me now tell you what's horrible about this. I've introduced a Q. What's the Q? The Q is a random null vector. Okay, so what does that mean? Q squared has to be 0, and that's all it means. Okay? It's a random null vector. It represents gauge dependence. So this has to cancel out. No Q can appear in your final expression. Okay? But this makes sure that no matter what gauge you're in, whatever gauge choices you made when you wrote down your amplitude, that you absolutely get physical stuff and only physical stuff. Okay? Yes?
I thought our propagator rule when we cut was that the propagator was just supposed to give us 1.
Yeah.
It's 1 plus this polarization sum?
So the propagator, so there was the cut rule that I'm applying to how I dress cut graphs, right? And so that's taking that big expression on the upper right over there and dressing a graph like this, but now I no longer get to write an S below, right? I just have 1. So I just have this cut expression. This is my cut expression that I got from taking my candidate dressing, my guess for 4-point, and evaluating with on-shell conditions. Now what I'm going to do is I'm going to match it to sewing together 2 lower point amplitudes, right? And what I'm explaining now, and I can't believe any of you can read this. Can any of you read this? Wow, man. Oh, the good eyesight of early career researchers. What did I even say? All right. Good. So all right. So you now, what I will say is many cases you don't have to worry about this. You're just good enough with eta mu nu, and you can sort of. But especially when you do multi-particle cuts at loop level, you have to be very careful. Now, the great thing about Dimitri, and this is why everybody should be friends with Dimitri. You want to raise your hand again? Hi, so everybody knows who you. The reason you should be friends with Dimitri is he can tell you how to always get away with using eta mu nu and not to have to worry about this, right? There are tricks, and he wrote a great paper earlier on in his grad school career about it. And this has been around for so long. It's really great that he had these insights. Anyway, but we're gonna use the projector that you should use if you don't know it's safe. In this case, it is safe. But all right. So let's see what happens when we plug this in. All right. Where can I go? I'll go to here. Yeah, sure. But then I couldn't drag that up, and that would be sitting low to the ground, right? So why don't I push this guy up and take this guy down, and I'll just start writing here. All right. All right, do people have a good feeling for the story we're telling here? What we're actually doing? We're taking things that are gauge invariant and physical, and then we're evaluating over all the possible options that they could have to speak to each other consistently. And we're seeing if that's consistent with what we think the answer is. Okay, so this is a verification. Now, as I said before, if you have a great way of verifying things, and this is a great way of verifying things, then you've got a natural way of constructing stuff. All right. Good. So states A, 1, 2, I, A, not I, 3, 4, E plus, plus, E minus, minus, state bar, quark plus, plus, quark minus, minus. Okay, good. So this is going to be U bar 2, gamma mu, V1, sum over states, epsilon mu I, epsilon nu minus I, U bar 4, gamma nu, V3. Okay. Does everybody see the thing I just erased? Ooh, a good judgment. 2 copies of them. Now I've moved the sum over states just to the inside, which is the only place it's relevant. Okay? And so what we're going to do is we're just going to plug in that projection relation below to here. And you'll see, okay, so let's plug it in. Eta mu nu minus Q mu I nu plus Q nu I mu over Q dot I. And that's what's going in to this middle right here. Okay? Yeah.
The notion of the gauge invariant projector here is if we like contract this with P or I view person.
Well, so let's talk about why this term has to vanish and why this term has to vanish, and it has to do with what the on-shell conditions say I is. What's I? What's I squared? 0. And it's K1 plus K2, or it's K3 plus K4. So what happens when I throw this guy into here, this guy into here? What do I get? 0. And what do I get when I throw this guy into here? So I can throw away this term, and I have no gauge dependence. So I wasn't missing any pieces. There are times where you have multiple diagrams contributing on various sides of the individual diagrams are not going to be gauge independent. This would need to cancel between diagrams. Okay? If I had multiple graphs on each side of the cut. Yeah? In this case, it just cancels right away. Okay, yeah?
And in this case, we only have one state that we're dealing with, right?
So gluons, let's say gluons in 4 dimensions, how many states do gluons have? 2, right? So if I was doing this in four dimensions, I could say I have, I plus, sewn with, minus I minus plus I minus I plus as the 2 states. All right. Now I'm keeping things formal and d-dimensional, right? But that's exactly what I've done. All right. And if I did this explicitly in 4 dimensions, I'd be doing just this. Okay. Good. Well. All right. So this goes away. And what does this do? It dots this with this, recovering this. Okay? So good. So we did it. We're consistent. Does that mean there's nothing else possibly that contributes at 4 points? It doesn't mean that at all. I just want to emphasize, we can always have higher derivative contacts that don't contribute to the cut, right? We could have scalar interactions between our fermions, perhaps in some theory, that we haven't addressed, right? So if at 3 points, for the theory we're talking about, we had scalar states, like we had some sort of Yukawa, right? Then we'd have to consider that as well, right? And what's missing? It would be stuff like that that's missing. Yeah.
So everything here you're doing on shell, but aren't there off shell pieces of the amplitude that should contribute?
Well, so not here, not here, but yeah, yes. So let's say I was doing this. Where am I with time? Oh, okay. Yeah, no, good. It's so I should make this point very clear. If I was doing this with gluons, right, and I just wrote down something goofy like if I just took and said this was equal to that. If I said, my numerator for this, and I just set it equal to the cut sewn product of these guys, my resulting amplitude over here wouldn't be gauge independent. It would be wrong. It would be garbage. It'd be missing a piece. What's it missing? It's missing the known 4-point contact that you get from expanding trace f squared. For those of you who know, when you expand trace f squared, you get a cubic and you get a quartic term, and it's a contact. And this contact is absolutely required for gauge invariance. If you don't have it, you're missing stuff. It turns out you can impose color kinematics on an ansatz here, and then you recover gauge invariance. But that's a...
So we have our 3-point on-shell amplitudes that we think are right, and we had a guess of what the 4-point amplitude would be. And we took the cut version of our 4-point amplitude guess and checked if it was the same as sewing together
the 3
points.
Right.
If they didn't match, would that mean we had made an incorrect guess for the 4-point one, or we hadn't included all of the ways of sewing together?
There's only sewing together 2, 3. But so if we had an error here, we'd have very deep trouble. We would have, there was just no freedom to write anything down consistent with our rules. It would have meant that I predicated everything on were garbage or incomplete at best. There'd have been a problem.
Is that true in the general case?
So in the general case, when you run into inconsistency, you're missing something. Yeah, and you need to figure out what that is, right? And this is called unitarity for a reason, right? That only physical stuff, that you're capturing all the things that are physical, right? If you're missing stuff, if probability is leaking out because you're creating states you're not accounting for, then you don't have the handle on the theory you think you're talking about. Good. All right. But let me again. Yeah. Oh, sorry. Yes. Thank you.
So can I think of this way as a kind of passive story, some over all the steps we do?
It is absolutely a free country. You can absolutely think of it as some sort of path integral. You should let me know how. Let me know if that works. Yeah, if you're asking if I think of it as some sort of path integral, I don't. But that doesn't mean it's. That doesn't mean that's the wrong way to do it, right? But the thing is, so using this and symmetries that you care about, like gauge invariance or color kinematics or Adler's zero or whatever, you can bootstrap up to all tree-level amplitudes. And once you understand tree-level amplitudes, because you're only allowing physical stuff to cross cuts, you can bootstrap up to all loop-level integrands without having to worry about ghosts. So there's an approach to perturbative quantization where you're only tracking physical information. Okay, and the reason I'm emphasizing. So usually when you hear amplitudes people talking about this and presenting these ideas, you're going to get a crash course in spinor helicity methods, and they're awesome. They're great. They're a great way of getting tree level data in a particular fixed dimension, okay? But if you're going to regulate your integrals with dimensional regularization to preserve gauge invariance, you can throw out information. If you construct things with just 4 dimensions, you'll get the wrong answer. And something just to convince yourself of that, I think, is the classical result that at one loop in pure Yang-Mills, you have a non-zero scattering amplitude between all plus helicity gluons. This is not true at tree level. At tree level, you have minus minus plus plus is the maximal helicity violation you can have at tree level, but at loop level it changes. You can have this, but if you try to construct this information purely in 4 dimensions, like on a cut, so since, as I said before, my trees, plus, plus, minus, minus is all it's non-vanishing over here. I can't have any pluses over here, otherwise this vanishes. But the second I have the minuses there, I have pluses over here. And so this vanishes. So trying to build this with 4-dimensional information, I get a 0. And so I'd say, oh, this doesn't exist if all I use was 4-dimensional information. But that's not true, right? I need to use d-dimensional polarization sum, right? I'm regulating with dimensional regularization. And then I get the right answer. The answer you get from Feynman rules. Yeah. So people used to call stuff like this, the rational terms are not cut constructible. What they mean is it wasn't cut constructible using only 4-dimensional information. Okay, but it is cut constructible using d-dimensional information. 15 minutes. Oh boy. Oh boy. Okay, great. So I'm gonna walk away from this example. If you have more questions about this example, absolutely ask them on Slack. If you want good test examples to play around with simple things to build an ansatz that are more complicated than this, then I can give you some problems on the Slack as well, like scalar QCD, like external scalars or 2 external scalars or 2 gluons, or even just 4 gluons. Okay, but to do it efficiently, let me get to this next part of the discussion. All right, and for this next part of the discussion, so you'll notice in this case, we did what's called a color-dressed cut. We actually kept, oh, I didn't write the color, haha, but we actually kept the color. But one of the advantages of working in gauge theories is that you can separate the color from the kinematics and still be talking about gauge invariant quantities. And so that's what I'm going to emphasize by going pedagogically, but in a spirited and fast fashion through 4 points. All right. And this is quite generic. My discussion is going to be quite generic for things that are charged in the adjoint, things that are adjoint type, but that's the most complicated case. Anything that's deviating from the adjoint starts throwing channels out. Like we saw, we didn't have 3 channels in our 4-point amplitude. We only had 1 channel, right? Because we had flavor that was protecting from drawing all the channels that would show up if you had adjoint. So adjoint is the maximally complicated, and that's what I'm going to talk about. And then you can select away stuff. Yes?
Sorry, I don't mean to derail you. Could you just repeat what you said about gauge theories, please? Because that felt really important when I didn't get it written down. Gauge theories, you can separate.
Color and kinematics. Yep, that's so that's the whole point right now. Okay, so 4 points, and so this is going to be adjoint type. So think Yang-Mills, but you could also think nonlinear sigma model, chiral perturbation theory, chiral Lagrangians, as long as I've got stuff that's charged in the adjoint. Okay, adjoint type. So 4 point. What channels contribute? If I were to talk in terms of Feynman diagrams and a contact, okay? This is the only things I can do, draw a tree level for 4 points, okay? tree level, no loops, no closed loops. All right, so I'm going to call this S. I'm going to call this T. I'm going to call this U. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to call this X for the contact. Good. So S K1 plus K2 squared is going to be the propagator. T equals K2 plus K3, 2 plus K3 squared. This propagator, U equals K1 plus K3 squared is this propagator. No propagator over here. Okay? Color factors, CS, F, A, B, C, D. Okay? And so internal lines, I'll just use E. Okay, and that's summed over. F, A, B, E, F, E, C, D. How did I do it? I just read cyclically around A, B, E, E, C, D. Yeah? I read cyclically around. C, T, F, D, A, E, F, E, B, C. Cyclically around. Yeah? F. This is CU. So F, C, A, E, F, E, D, B. Okay? Ooh, I didn't say something important about U. U equals minus S minus T for on-shell massless. Okay, this is important, right? On-shell, conservation of momentum means U equals minus S minus T. These guys obey a Jacobi relation. CS equals CT plus CU. Okay? Good. Now, this contact guy, we're going to move them into a cubic skeleton framework, so then we can start talking universally about all sorts of things. And I will explain those words as soon as I'm done erasing. So, what is the contribution of this contact? Okay, so generically, it's going to look like CS times some x to the s plus CT x labeled t plus CU x labeled u. Maybe you'll remember from Feynman rules that you'll have something that looks like FABE, FECD, like eta Muon, eta mu, some eta contraction indices, plus the other guys, CT, some contraction of stuff, plus CU. Eta contraction of stuff, eta contraction of stuff, right? You can open up Peskin and Schroeder, look at the 4-point vertex, right? And it's just be some contraction stuff times CS plus CT plus CU. Is this unique? It is not unique. It's not unique because CS equals CT plus CU. So I can move stuff around, right? That's a gauge choice, is to move stuff around. Yeah? I just want to emphasize there's nothing unique about this. Good. What do I want to do? I want to write things in terms of cubic graphs. So my amplitude right now looks like CS over CS NS over S plus XS plus perms, right? Plus all the, CT and CU. Good. What can I do? I can pull the S out, equals CS over S, NS plus S times X of X, right? I have done nothing. I've done nothing interesting, right? I just pulled this S out in front of both, and so I need to multiply by S here, so all I did was multiply by 1. Yes? Okay, but now I can call this NS twiddle, and I'm describing my entire amplitude in terms of things of cubic diagrams. All right, plus perms. NS twiddle, CS S plus NT twiddle CT over T plus NU twiddle CU over U. Okay, I've done nothing fancy. I just multiplied my contact terms by 1 in the form of S over S or T over T or U over U just to assign it to cubic graphs. Is it unique? Not at all. Why? Because CS equals CT plus CU. So it's possible to move information between these cubic graphs. Okay? Good. Is this by itself gauge invariant? No, it is not. It's just an individual diagram. Individual diagrams don't mean anything. Why? It's because I'm not in a color basis. Okay, but what I can do is I can use this, for example, to write CT equals CS minus CU. And CS and CU have no relation between them. They're pointing independent directions in color space. So what does this look like? You know what? I don't have time. Let me just do this. So what does it look like? It looks like A4 equals CS NS over S plus NT over T plus CU and U over U minus NT over T. Right? Plugging in CT equals CS minus CU, right? Everybody understand what I did? I went to a color basis, a minimal color basis, right? So this is pointing one direction in color space. This is pointing a completely independent direction in color space. Yeah? So this thing has to be gauge independent because it can't cancel against anything over here. Oh, yeah, good question. I wasn't going back to dropping my contact. I just got lazy. Independent direct, right? So these gauge independent. And this is what Amplitudes people call color stripped or color ordered amplitudes. So this is a full amplitude. This is an actual amplitude. This is an actual amplitude. This is a partial amplitude, but it's gauge invariant. It's a gauge invariant building block. Okay? So I could call something like this a, ST just to label the channels if I wanted to. Or you might see it more often written as A1, 2, 3, 4. Now, full amplitudes, curly A. This is going to be a nice big Roman A for ordered amplitudes. Okay? And why are they called ordered amplitudes? They only have two. So 1, 2, 3, 4 plus 1, 2, 3, 4. Right? The S channel and the T channel. And you'll notice as you just go around this structured graph, both diagrams have the same order. Right? 1, 2, 3, 4. 1, 2, 3, 4. Okay? Let me write down the ASU, right? Sorry, TU. This is a TU diagram. A 1, 3, 2, 4. So again, but now we'll just write it as 1, 3, 2, 4. 1, 3, 2, 4. And this is a lot like what I've called NT, the T graph over here, except what's different is this vertex is flipped. Right? This vertex. See? Let me write this very big. 2, 3. 3, 2. Right? For this to be bow symmetric, For this to be mode symmetric, if this guy picks up a minus sign, then this has to pick up a minus sign. If I flip a vertex into my FABCs, I get a minus sign. So this has to be equal to okay, which is why it's a minus NT over T. Okay? Good, yeah.
I followed you up until we established this color basis. You magically got this staging kind of thing. I'm going to look at that later. Then, what did we write down?
Oh, okay. So, all right. So the reason this has to be gauge invariant is because these guys generically in generic gauge groups don't speak to each other. They're just pointing in different directions. Since they don't speak to each other, there's no way for gauge dependence here to cancel with gauge dependence here. So they have to be gauge independent. All right? We're going to call something like this, we're going to call it an ordered amplitude. Right? So you can call it a color ordered amplitude or a stripped down ordered amplitude. Okay? And the reason we call it an ordered amplitude is because a subset of channels contribute, and the only channels that contribute have a consistent color ordering on the external legs. The only channels that contribute have a consistent color ordering on the external legs.
We recognize the ones that this was the Jacobi identity. Are there any others that we kind of need to know a priori?
Not for adjoint. For adjoint, it's just antisymmetry and Jacobi. Okay? And so you can always, so once you've got things in terms of cubic graphs, you can always go to a color basis, a minimal color basis, solving the linear Jacobi relations between the color weights, and whatever's sitting out in front of these independent directions in the color space is an ordered amplitude. Okay? Yeah, if for SUN, you get these same ordered amplitudes if you go to a trace basis. You can go to a trace basis for SUN, but I prefer to keep things in a cubic basis because it makes my life doable at loop level. So I'm going to stay in a, but you get the same ordered amplitudes for adjoint when you go into the trace basis.
So I'm also a little confused by this.
Yes.
So I see that these diagrams have the same 1, 2, 3, 4 ordering.
Mm-hmm.
My confusion is why, for example, this thing you've drawn as an S channel with a 1, 3, 2, 4 ordering. That's
Mm-hmm.
a channel and the other.
Yeah.
How do I know which side it should go on? I guess which piece it should belong to.
Well, so what I've taken is something that has a U channel and a T channel, right? A U pole and a T pole, right? And this, what's sitting here came from my convention for what I called CU and what I called CT and what I called CS, and which basis I went into, right? I could have. Let me introduce a CT bar where I just flip one of these indices, F A D E F E B C. So I just flipped these two guys, right? I could have defined something with a CT bar, right? Then my colors don't satisfy this. They would have satisfied a CS plus a CT bar equals CU, right? And I could have moved the CU over so everything's nice and symmetric by flipping one of the U's. Here, I'll pull this up just so, right? So if I flipped this guy, then this has a minus sign relative to this. So I just move it over, right? It's just a convention of what I called it, and it doesn't matter at all. But what it defines the signs that start showing up, And again, I didn't rely on any relations between ends. All I did was just straight up color manipulation, and I went to a basis. And then you just see what channels are sitting next to you.
So I see how to do that from this equation. I guess my question is, if I wanted to start from drawing these diagrams.
Yes, good.
How would I figure out which one?
Exactly. I'm just about. I'm gonna. That's great. But where and you'll get to hear about that tomorrow morning. Yeah, you'll get to hear about that tomorrow morning. Yeah.